Hey folks, welcome back. In this video we're going to look at ray diagrams, so let's get started. Now again, ray diagrams were seen in the waves topic for National 5 Physics when you looked at refraction, but we're going to look at them again for higher physics. So a ray diagram, remember, is where we draw rays to represent light travelling. And we have different parts of a ray diagram here, so remember the normal is a dashed line that is drawn perpendicular at 90 degrees to any surface. We then have the angle of instance, which is labelled little I, and this is the angle measured between the incident ray and the normal. And we also have something called the angle of refraction, which can be labelled little r, and this is the angle measured between the refracted ray and the normal. So to put this into context, let's have a look at the diagram here. So here's our normal, this dashed blue line at 90 degrees or perpendicular to the surface of the block. We've then got air on the outside, and this is our glass block here. And we've then got this ray going into the block, which remember we call the incident ray. And we've also got this ray within the block, which is slowed down, called the refracted ray. And if you were to continue the line and draw a ray going outside of the block at this side, you would call that the emergent ray because it's emerged on the other side of the block. And remember we said the angle of instance I is the angle between the incident ray and the normal. So that's going to be this angle in here. And then the angle of refraction R, remember, is the angle between the refracted ray and the normal. So that's this little angle in here. It then says if light enters a new material and slows down, the angle of refraction is smaller than the angle of instance. However, if light enters a new material and speeds up, the angle of refraction is larger than the angle of instance. So if we look at our diagram in this case, notice how we've got light entering the new material and slowing down because we've got air into glass. So that's this first case here. So the angle of refraction here should be smaller than the angle of instance. And you can see that in the diagram. We've got a smaller angle of refraction there than the angle of instance there. However, if we were to continue this light to the other side and then show the emergent ray refracting parallel to the incident ray, then we could draw another normal at this point, and we could show that in this case the angle of refraction would be larger than the angle of instance. Now I'm just going to show you a few simulations to help you visualize this. Now I did show this simulation in the previous theory video on refraction, but I think it's worth looking at it again in terms of ray diagrams. So if I click play here, we'll see some straight line waves called planar waves or wave fronts, which remember represent the crests of waves. So that means the distance between any two adjacent wave fronts here, or two adjacent crests, gives you the wavelength. Because remember, wavelength can be defined as the distance from one crest to the next crest. So that's the wavelength there between the waves, and we can see what happens to that wavelength and the speed of the waves as they pass through the block. So notice how the waves are slowing down as they enter the block. They're also changing direction when they enter this block here and when they leave the block. And we can see that the wavelength is changing as well. So the waves are bunching up within the block and they're spreading out again when they leave the block. So that means our wavelength is decreasing inside the block and then increasing when the light leaves the block. And to make this a ray diagram, we can label the rays on there. So first of all, we've got our normals, which are shown by these green dashed lines. We've then got our incident ray on the left-hand side. We've then got the refracted ray inside the block, and then the emergent ray upon leaving the block. We've also got our angles of instance and refraction labelled here. So remember, the angle of instance is measured between the incident ray and the normal, so that's this angle here. And we've got the angle of refraction, which remember is the angle between the refracted ray and the normal, so this little angle in here. And notice how, because we're going from a less dense material to a more dense material, the angle of instance is greater than the angle of refraction. However, on this side, we could see that the angle of instance is this angle in here between the normal and the incident ray, and that's now the incident ray on this side of the block. And we could say that for this normal, this is the refracted ray. So this is our angle between the refracted ray and the normal. So when we go from a more dense material to a less dense material, the angle of refraction here is greater than the angle of instance. Now just a quick reminder of what happens when light passes through a semicircular glass block instead. Well, if we draw the normal at 90 degrees or perpendicular to the flat surface of the semicircular block and then pass light along the normal, notice how the light's going to pass straight through the semicircular glass block. And this is just like what we saw for the rectangular glass block. So anytime light passes along a normal, it's going to travel in a straight line. And remember in National 5 we said that any point along the curved surface is actually a normal, because whenever light passes through this curved edge, it's going to be entering or leaving at 90 degrees to that edge because it's curved. But what happens when we increase the angle of instance to be greater than 0 degrees to the normal? Well, if we increase the angle of instance, notice how we get some change in direction going on. So in this case, the light's coming in at 67 degrees, so our angle of instance is 67 degrees. And then we've got an angle of refraction inside the block of 37.8 degrees. So we've got this change in direction where the light comes in, bends towards the normal, but then passes straight through the curved side, because remember, any point along that curve is going to be a normal. So you could draw a dashed line here to show the light's going to pass straight through the curved edge. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.